Hello again, everyone, and welcome to Exponential Word Problems Day 2. So today we're going to try and run through these notes a little quicker. I know yesterday was pretty long because the notes were long, but hopefully all of the information made sense and what we were doing was making sense as well. So again, we are going to be working with the exponential form y equals a times 1 plus or minus r raised to the power of x. That plus or minus is dependent on whether we have a growth or a decay taking place. A, once again, is our initial value. R is the growth or decay factor. And remember that we're given a percent, and we're going to change it to a decimal. And then last but not least, our x value is our time. All right, let's take a look at number 1. A 3-bedroom house in Pittsburgh was purchased for $190,000. If housing prices are expected to increase 1.8% annually in the town, write an explicit formula that models the price of the house in T years. Find the price of the house in 5 years. All right, so this is a two-part question. We're first going to write a formula that models what's going on with the housing price, so it's obviously going to increase over time, and then we're going to use our formula to find what the house will be worth or how much it will cost in 5 years. So just picking out some key information here. Purchased for $190,000. That's our A. It's expected to increase, so this means it's a growth. And it's increasing by 1.8% annually. Okay, so 1.8% increase, that means this is a growth factor. I'm going to turn 1.8 into a decimal. Oops, and I get 0.0. Oh, you did not erase for me. There we go. 0.018. Okay. Last but not least, our x is going to be number of years because we are increasing annually. Okay. So let's put together our equation. Y equals our a value times 1 plus, because it's a growth, 0.018 raised to the power of, oh, and I'm sorry, instead of x they want us to use t, so let me just switch that out because they're talking about t years. There we go. Alrighty, so simplifying this just a little bit, at 1.018 raised to the power of t. So here is our explicit formula that models the price. So the price of the house I represented with y, and t is representing how many years. So we are looking for the price of the house in 5 years. So that means our t value, so we're going to use a t value of 5 in this case. All right, so plugging into our formula that we wrote, I'm going to replace t with 5, and I'm going to go to my calculator. 190,000 times 1.018 raised to the 5th power. And we are looking at, so I'm going to give you everything that I see on my calculator right now. 207,726.7809. Now remember with this, we are talking about money. So what I'm going to do is I'm going to round this up just to the nearest whole dollar. So I'm going to say the price will be approximately, since I'm rounding, it's going to be approximately $207,727 since we're going to round up here. All right, so that's approximately how much the house will be worth in 5 years if it continues to increase in value. Number 2, in 1990, there were approximately 5.4 million people in the world. If the population grows at a rate of 1.95% per year, Estimate the population in 1999. Okay, so we start in 1990. There was 5.4 billion people at that time. So that's my A value. And I am going to leave it as 5.4 for now, so our answer will be in terms of billions of people. If the population grows, so that means we have a growth rate of 1.95%. Let's turn that into a decimal. So 1.95%. I know it's a little strange because you see a decimal, but this is technically a percentage value, 1.95%. So we want to take this percentage out of 100 and turn it into a decimal out of 1. So dividing by 100 or moving the decimal place 2 to the left, we get 0.0195. And again, this is our growth factor here. Okie dokie. Next, our time frame, we're looking at per year, so number of years. And in this case, I am going to stick with X. You're more than welcome to use T, whatever you feel most comfortable with. Okay, let's first put an equation together. 5.4 times 1 plus 0.0195 raised to the power of X. And simplifying this, I get 5.4 times 1 plus what am I doing? Simplify. There we go. Okay, now the question asks, estimate the population in 1999. All right, so our X value, and I should include number of years since 1990. I'm going to put that in there as well. So how many years past 1990 is 1999? Well, 9 years. So we're going to plug in an X value of 9, and we're going to estimate the population. So 5.4 times 1.0195 raised to the power of 9 gives us, and I'm going to write down everything that's on my calculator right now, and then we will round in just a second. So 6.4250843 Okay, so here's what I see on my calculator, and I'm actually going to follow kind of my rules that I did yesterday when we used the population question from, I think it was question number 5. I'm going to round to 4 decimal places just so it gives me the best picture as far as what this population will be. So in this case, we could round up, we could say a nice round 7 billion if we wanted to, but since we were given, or really, yeah, we'll go 4 places because I think it'll be more accurate. We'll extend this out. We'll say approximately 6.4251, and remember this is actually billion, not million, but billion people in the world. Okay. All right, so that's just a little review from yesterday. Today we are going to take a look at something a little different, but it still falls under exponential functions. Whoops. So interest. So if you guys know or have a bank account or a savings account and you receive interest on the money that's in your account, this is basically the bank giving you money because you opened an account with them and you have money in an account with them. Now, interest, you will typically hear about interest being paid out once a year, right? So a lot of times in many math problems, you'll see that up until this point anyways, you'll see that interest has been paid out once every year. But sometimes that's not the case. Sometimes banks will provide what's called compounded interest. So what this means is your interest is compounded, or I should say you receive interest payments daily or weekly or monthly. So you're actually receiving interest or payments into your account more frequently. So there is a particular formula that is used when we talk about compound interest, and that is this interest right here. Okay, so we're going to have n represent the number of times that your interest is compounded per year. So instead of having, like I said, that one payment in interest into your account per year, you might be receiving this payment, or I should say you might be receiving interest more frequently throughout the year. Like I said, maybe daily or weekly or quarterly, again, quarterly 4 times a year. So you could be receiving that interest payment, again, more frequently as opposed to just one time per year. So you deposit $1,000 in a savings account that pays 8% interest annually. Find the balance after 4 years. If interest is compounded annually, compounded quarterly, or compounded daily. Okay. So let's first just pick out some key things that we have here. So the first thing is we have our deposit of $1,000. This is going to be our A value. Next, we know that it pays 8% annually. Okay, so 8%, this is a growth factor because you are having money put into your account, so your account value is going to go up. So this R, our growth factor, turning into a decimal, is 0.08. And then in this case, our T value, I'm trying to use the variables that are in our equation that I just gave you. So our T represents number of years because, as it says up here, it's compounded per year, and here it says 8% annually. Okay. All right, so we're going to find the balance after 4 years if the interest is compounded annually first. So we're going to start with part A. So annually means you'll receive interest one time, an interest payment, one time throughout the year. So you'll receive one interest payment. It's going to be about 8% of what you have in your account. So looking at this, annually again just means one time per year. Okay. So our N value, N is going to represent the number of times it is compounded yearly. So I apologize, that blue circle should have been down below. So the N represents the number of times that we're compounding the interest. So when is our interest applied to our principal? It's going to be compounded, or it's going to take place once per year. Okay, so our N value in this case is 1. Okay, so plugging in basically all the things that we have into this compound interest formula, y equals our A value, which is 1,000, times 1 plus our R value, so now we have 0.08 over our N, which is 1 because we're compounding annually, one time per year, and then raised to the power of 1 times T, which in this case, our T value is actually 4 because we're trying to find the balance after 4 years. So T is 4 in this case for each one of these problems. Okay, so this looks a little yucky. I'm going to try and simplify some things here. So 0.08 divided by 1 gives me 0.08. 4 times 1 is 4. Again, just continuing to simplify so that I can put something nice into my calculator. I'm going to take $1,000 multiplied by 1.08 raised to the power of 4. And how much money will be in my account after 4 years if we're compounding interest annually? So I'm going to have $1,360. Now I'll give you the full decimal that I see on my calculator, but we are obviously going to cut that down because we're talking about money. So we'll say approximately, and we're going to round to 2 decimal places, $1,360.49. So if I don't add any additional money to that account, if I just put $1,000 in and I just keep collecting interest over 4 years, if I receive interest once a year, then I'm going to have $1,360.49 in my account after 4 years. But what if interest is compounded quarterly? So quarterly, if you think about, there's 4 quarters in a dollar, right? So quarterly actually means 4 times per year. So quarterly means 4 times per year. And in this case, that means our N value is 4. Okay, so that's the only thing that's changing is our N value. So plugging in, our A stays the same, our R stays the same. Again, N is now 4, and I'm just plugging into that formula that you were given in the box above, raised to the 4 times 4 now, because it's N times T, 4 times 4. All right, so simplifying a bit here. 1 plus, so 0.08 divided by 4 gives me 0.02, raised to the power of 16. So continuing to simplify. Now you can actually put what we had above there, you could put that right into your calculator. You don't have to actually do the addition first. I just like to because it's just less that I have to type into my calculator, but don't feel like you have to follow what I'm doing. Alrighty, so if we compound our interest quarterly, so we're receiving interest 4 times per year instead of just 1. Here's what I have on my calculator. And again, we're going to cut this down because we're talking about money. All right, so it looks like in my account, I'm going to have approximately $1,372.79. So if you notice, the more often it's compounded, the more money I'm going to end up with in my account. Not a ton more, but it looks like at least $12.30 more, so not too bad so far. What if we're compounded daily? So what if that interest is applied daily? So daily, think about how many days are in a year. 365 days. So that means per year. So that means our N value, how often it's compounded, is 365 times per year. Okay, so plugging into our formula, once again, y equals 1,000 times 1 plus 0.08. And remember, the only thing that changes each time is our N value. That's the only thing that's changing. R stays the same, T stays the same, your A stays the same, all of that stays the same, it's just N. Now when I take, so this might be one of the ones where you may want to plug this into your calculator actually the way it looks here. So I might leave this because when I do 0.08 divided by 365, I do get a pretty small decimal. But it does continue on for a bit, so I'm going to leave this. And then 365 times 4, that gives me 1,460. Okay. So I'm actually going to plug this right into my calculator. Now the 0.08 divided by 365, that one you have to be careful with. So let's see. We're going to go 1,000. Parentheses 1 plus, now you could, if you wanted to, you absolutely could use 0.0002. I'm just trying to be as accurate as possible. So I'm going to use kind of double parentheses here. I'm going to put that 0.08 divided by 365 in its own set of parentheses within that parentheses for your B value. And then I'm going to raise it to the power of 1,460. So I kind of used double parentheses there just to make sure I was really accurate. So basically I did this in my calculator. I kind of double parenthesed it. Okay, so what am I going to have in my account at the end of 4 years if we're compounded daily? Oops, that's supposed to be 4. There we go. And again, rounding this to 2 decimal places because we're talking about money, we're going to have approximately $1,377 and a whopping 8 cents. There we go. So you can see the more often our interest is compounded, the more money will end up in our account. All right. Okay, so let's kind of go back to yesterday. Okay. So we're going to put a hold on compound interest for a second, and let's just go ahead and keep working with that familiar formula that we had yesterday, and actually that we've been working with throughout this entire section here. So you buy a car for $24,000. The value of the car depreciates by 16% each year. All right, here's our A, here's our R. Depreciates means it's a decay factor each year. That's our time. So just for the sake of time here for you guys, A, R equals 0.16, and X equals number of years. So I won't write it on the side, I'll just go ahead and write the function right away. So write a function that will model the value of the car in X years. All right, so this is a decay function. So when I write this, I'm going to say Y equals starting value of 24,000 times 1 minus our R value raised to the power of X. Now in place of Y, you are welcome to use f of X. Okay, you're welcome to use function notation if you would like. And then I'm just going to simplify this a little bit. And we have our function. So now if we want to find out what the car is going to be worth after 2 years, that's giving us an X value. So we're going to plug in an X value of 2 into our function that we wrote above. And let's see what we get. So 24,000 times 0.84 raised to the power of 2. So the car after 2 years is going to be worth, well, let's see, $16,934.40. Okay. So you can see the value of the car went down. Sadly, that is the case, but it is a very realistic case when it comes to car buying, sometimes even home buying. All right. Number 5, you deposit $1,500 in an account that pays 5% interest yearly. How much money do you have after 6 years? Okay, so notice how it does not say compounding at all. So we're not using the compound interest formula. We are simply going to be using our regular formula that we've been using for exponential functions. Our deposit of $1,500 is our A. Oh goodness, excuse me, hang on, that looks terrible. Okay, here's A, here's R, interest yearly, that's our X. Okay, so how much money do we have after 6 years? So this is when we have an X value of 6. So putting our equation together, and we can actually just go ahead and go right to the step of, now when we talk about interest, we are talking about money being added to our account, so this is a growth. So we're going to say 1 plus 0.05 raised to the power of 6, because we're talking about over 6 years. So just simplifying a little bit before I plug into my calculator, I'm going to go ahead and do that. Raised to the power of 6. And I get, and again, we're going to approximate this because we're talking about money. So there will be approximately $2,010.14 after 6 years. Approximately $2,010.14. Okay. Going on to number 6, if you have $500 in your account after 4 years, investing at 2.5% per year, how much money did you start with? This one's interesting. Okay, so with this one, we have $500 in our account after 4 years. So we're actually given our total value. We're given an output right now. We're given a y. So this is a y value right here. Y equals 500. After 4 years, that's time. So our x was 4. Investing at 2.5% per year. This is our growth rate, because remember, whenever we're investing or we're talking about interest, we're gaining money. So our rate was 0.025. And then let's see, how much money did you start with? So we're actually looking for A. We don't know A. So if we were to kind of put this equation together, just with the pieces that I know, I'm looking at this. I'm looking at 500 equals A times 1 plus 0.025 raised to the power of 4. Okay, so let's go ahead and solve for A here. So we can do this. So 1.025 raised to the power of 4 is kind of a yucky decimal here. So I'm going to take this value. I'm actually going to try and almost leave it in my calculator. I'm just going to say, let's divide all of this by 1.025 raised to the power of 4 here. All right, so let's plug that into our calculator, because 1.025, again, raised to the power of 4 is a very long decimal. So 500 divided by parentheses 1.025, close the parentheses, raised to the power of 4. If you have your graphing calculator, your Nspire calculator, you can absolutely use the fraction key just to make sure that you're plugging everything in correctly. And here's what I get. So we're going to have to round a little bit here. So how much money did we start with? Okay, so I'm getting this for A. So I'm getting 452.9753224. But again, since we're talking about money, I'm going to round this. And I'm going to say approximately $452.98. So that's how much we started with. After 4 years investing at 2.5% per year, we ended up with $500. Okay, a mouse population is 25,000 and is decreasing in size, oh thank goodness, at a rate of 20% per year. What is the mouse population after 3 years? All right, so we're starting at 25,000. Thankfully, it's decreasing in size at a rate of 20%. So here's A, here's R, and 20% as a decimal is 0.2 per year. This is our X, number of years. What is the mouse population after 3 years? So we want to plug in an X value of 3. Okay, decreasing. This is a decay factor. So writing our equation, 25,000 times 1 minus 0.2 raised to the power of, instead of X, I'm just going to say 3 because I know that I'm looking for the population after 3 years. So 25,000 times 0.8 raised to the power of 3, going ahead and plugging that into our calculator, we get 12,800 mice. Yuck. I know they're good and we need them and all of that good stuff, but still, I don't want them around my house. All right. Let's take a look at number 8, last but not least. The population of a city grows at a rate of 5% per year. So this is a growth factor. That 5% means we have an R value of 0.05, and our X is in terms of years, so number of years. The population in 1990, so in 1990, was 400,000. Okay, here's our A. What would be the predicted current population? Okay, let's start there because this is a two-part question. So I'm going to split my page in half here to answer each one. So what would be the predicted current population? Okay, so what year is it? It's 2020. Okay. So if we're talking about the current population, we're looking at 30 years past 1990. So we're looking at an X value of 30 that we're going to be plugging into our equation. So our A value to start, we're going to have 400,000. That's our starting point. We're growing, so plus 0.05 raised to the power of, we're looking at 30 years past 1990. Okie dokie. So y equals 400,000 times 1.05 raised to the power of 30. Go into my calculator. Okay. So I'm going to give you what I'm seeing on my calculator right now. 6.95. Now, this isn't talking about, notice how it doesn't say anything about population, you know, in millions, in thousands. This is actually down to an actual person. So since we don't want to talk about 0.95 of a person, I'm going to actually round this up. So I'm going to say approximately 7, and I'm going to round this up to 7 so that we can include that whole person into our population. So instead of saying 0.95 of a person, we're actually going to round that up. When we're talking in terms of population, we're going to round that up to just a nice even 1,728,777 people. Okay, so now let's go on to the second part of this question. In what year would we predict the population to reach 1 million people? So remember, this is an output value. So 1 million is technically a Y value. And it asks us, in what year? Now, what represents number of years? X does. So we're actually going to be looking for an X value. Now, we are not going to get into, you're going to do this more in Algebra 2, but we are not going to get into how to solve for X when we have exponential functions. Instead, what we're going to do, the Algebra 1 version, we're going to use our calculator. So let's go ahead. So I'm going to type this in. So hang on, sorry. Getting our equation here, so I'm just bringing it over from the other side, and instead of 30 I'm going to say X because X is really what we're looking for. In your calculator, here's what I would love for you to do. I would love for you to type in the function, so graph it if you will. Let's graph the function 400,000. This is what you're typing into your calculator, just the right side. So go ahead and graph 400,000 times 1.05 raised to the power of X. If you want to look at the graph first, you should see a nice increasing exponential function. We're going to look at the table to help us come up with our answer here. So remember, our Y value is talking about our current population. So if I look at my table, X is years, Y is population. So when X is 0, this was the population in 1990. It was 400,000. Yep, that's what my table says. In 1991, so 1 year after 1990, the population was 420,000. 2 years after 1990 or 1992, the population's 441,000. So just giving you an idea of how we want to read this table. So I'm going to go ahead and I'm going to scroll down and I'm going to wait and see when I finally reach a y value of 1 million. And you'll see on your table, it looks like after 19 years, or I should say 19 years after 1990, we finally reach a y value. You see how it says, I know on mine at least, it says 1.01 and then it has like this E there. Okay, that 1 point means, look, we've made it to the 1 million. That E is scientific notation. It means times 10 to the 6th power. So we would move that decimal place to the right 6 times. So we finally, all right, so 1990 plus 19. So looking at 19 years after 1990, we are looking at the year 2009. So in the year 2009, we finally surpassed the population mark of 1 million. All right, and that's the end of Exponential Word Problems Day 2. We'll see you tomorrow for Word Problems Day 3.